So we're going to talk about the second proof in chapter 1.5, the Boreal measure. So let me state the theorem. It's called theorem 1.16. So it has three statements. So if f is from R to R, is right, continuous, and increasing, then there exists a unique Boreal measure on Boreal measure on R such that we have a formula. So mu, let me call it mu f, right? Mu f of AB is equal to FB minus FA. If there exists a G, if there exists such G, then F minus G is a constant. Moreover, if mu is Boreal measure, on R that is finite on all bounded Boreal set, then finite on all bounded Boreal set, then so we define fx is equal to mu of 0 x if x is larger than 0, if equal to 0, negative mu of x0 if x is more than 0. Okay, then f is increasing and right continues and mu f is equal to mu. So we're going to prove this theorem. It has a very close connection with theorem 1.14, which is the last step of constructing of measures. And it also talks about the uniqueness of the measure under the condition, for example, that the pre-measure mu naught is sigma finite. So we are going to prove this. How are we going to start, right? So we are going to so let me state my thought, right? So I want to prove there exists a unique Boreal measure on R. Well, by theorem 1.15, we know the existence of the pre-measure and on the algebra generated by the H intervals, and the sigma algebra generated by the algebra is called the Boreal sigma algebra. I think by one of the propositions in section 1.2. Okay, so since we found the existence of the pre-measure on the algebra, by theorem 1.14, and we also know that this pre-measure is sigma finite. So by theorem 1.14, mu, which is the outer measure induced by the pre-measure and only restricted on the Boreal system algebra, is a unique extension of mu naught. So therefore, and then we also observe that the interval AB is actually in is an H interval, and notice that the collection of finite disjoint interval of in the H, the finite disjoint union of H intervals, the collection of that is an algebra. And therefore we see that the interval AB is actually bound to the algebra. Therefore we can directly apply the definition for the pre-measure on the AB. Therefore we have mu F of AB is equal to FB minus FA. Let me try to write it down. So F is, so the first thing we're gonna use is 1.15. So F from R to R is increasing and right continuous. Okay, and therefore, so proposition 1.15, there exists mu naught pre-measure on A, on the sigma, on the algebra. Okay. So recall the outer measure is defined in the way that infimum is equal to 1 to infinity mu naught mu j. Mu j is in A, mu j. And mu naught, mu star is restricted on M, which is where M is sigma algebra generated by A. Okay. Is a measure on so we actually the real measure on R. Right. So and then we call this the real measure. Right. Since so I think so is generated by the H intervals A, B for A and B in R. I think by proposition in 1.2 section, M is equal to Boreal measure here. It is equivalent as a sigma algebra generated by open set of an R. So we know this is a Boreal measure, and then because mu star restricted on M is a measure on M, or we actually rename it as Boreal measure, Boreal sigma. Since it is a measure on Boreal sigma algebra, we call it Boreal measure. Okay, moreover, since R is equal to union negative infinity to positive infinity of j comma j plus 1, and mu, there is this supreme measure. Let's denote this mu naught f to denote to specify this deduced from the specific function. Mu naught f sigma finite. We want to show that the sigma finite j plus 1 is equal to, using the definition of the pre-measures that we constructed in proposition 1.15, this is equal to, so this is actually equal to supremum of j plus 1 using the definition I gave rather than definition in the book. So this is equal to mu naught f of, never mind. So this should be AB in j plus 1, okay, and then AB. So this is equal to mu naught j plus 1, and this is equal to 1, which is finite. Therefore, mu naught f is sigma finite, and by proposition 1.14, the theorem, by sigma theorem 1.14, we have what? We have mu naught f. Oh, right. We have so we call this measure mu star BR. Let me just rewrite it. Mu star of M, where M is a ultra measurable sense, is equal to mu star of B of R. Okay. We have this implies this. Okay, we have this equals to this. Is please really confused. Let me just is finite. Okay. Mu 0 f is sigma finite implies this is, no, this is unique, sorry. Is unique extension of mu naught f to a measure on that means if you on PR, if you have like this, so this measure is the same as the measure mu naught f on this on the algebra, right? So if you want to extend that to the sigma algebra, so this is the only function who is the extension of that algebra. Okay, so therefore we prove the first claim, right? There exists a unique Boreal measure. And also we need to prove this. Well, notice A, B using E is in the algebra. So mu star E R is E of E, of A, B is equal to mu naught F of A, B, and which is equal to sup of A, B mu, I'm sorry, CD, that is a subset of AB of mu of CD, which is just equal to AB. Okay, we prove the first one. And now, so 1, 2, 3. So 1. And we want to suppose suppose there exists a G such that F minus G is equal to K, then mu naught F of AB is equal to mu, well, by definition, it is equal to FE minus FA, right? And it is equal to, I think so FB minus FA is equal to GB plus K minus GA minus K, which is equal to GB minus GA, which is equal to mu naught GAB. And then, so this is kind of this direction, and this is this direction. So suppose mu naught F is equal to mu naught G. We want to show F minus is equal to K. Okay, let me show that. So by theorem 1.14, since something sigma finite, mu naught F is sigma finite. Mu F is the unique extension of mu naught F, and similarly mu G is the unique extension of mu 0 G. Okay, so what we have here is this is sigma finite, mu F is the unique extension of mu F G. Mu G is the unique extension of mu G. And that implies mu F, mu F is equal to mu G. Okay, and then mu F that implies FB minus FA is equal to G B minus G A. That implies F minus G is a constant. Okay, so now we need to show the last one. If mu is a Boreal measure on R is finite on all bounded measurable sets, so we define this. So first of all, let's show F is an increasing red continuous. So F is increasing, and the right continues. Okay. How do we show that increasing? Let's say increasing that x1 smaller than x2. There are maybe different cases. Okay, it's larger than 0, then fx2 minus fx1 is equal to mu of 0x2 minus mu of 0x1, which is equal to mu of 0 x 2 7 minus 0 x1, which is larger than 0, which is equal to, okay, mu of x1 x2, which is larger or equal than 0. And then let 0 x1 x2, so fx2 minus fx1 is equal to because mu 0 x2 minus x1, what is fx1 is negative mu x1 0. Okay, it is equal to mu 0 x2 minus or plus mu of x1 0, okay, which is equal to mm, mm, so this is equal to 0 x2 union x1 0, okay, which is larger or equal than 0. Okay, let x1 smaller than x2 smaller than 0, then this is equal to this. So x2 minus x1. Okay, so this is equal to mu of x2 0 negative plus mu of x1 0. Okay, so this is equal to mu of x1 0 minus mu of x2 0. Okay, so this 0 x1 this is x2, this is x1. So x1 0 minus x2 0. So this is equal to x1 x2, okay, which is larger or equal than 0. So it is increasing, and now we need to show this right continuous. how to show right continuous is xn converges to x from right. Um, fxn minus fx is equal to let's see that x is larger than 0, then mu of 0xn minus mu of 0x is equal to it is equal to okay, how about I do this? Is equal to mu of 0xn is equal to is equal to mu of 0xn mu of let's see. Oh, the limit, sorry. Right, the limit. And then because xn continuity from below, okay, so this is equal to intersection of 0x and which is equal mu of 0x, which is equal to fx. And if x is equal to 0, that's fine. If x smaller than 0, then xn also converges to x. Just 0 here is x, and we are doing this, right? I think the same f xn is equal to the limit of mu of x not 0x and the limit negative mu of negative no x and 0, right? So and this is equal to negative the limit right mu of x and 0 and is equal to xn as n converges to x. It is so my xn could be something like this, right? So it's increasing sequence. So it's limit of mu union of x and 0, and it is equal to negative, so negative mu, let me get rid of this limit, mu of x0, which is equal to fx. Okay, so we showed this, and then the last thing we need to show is we show mu f is equal to mu. Okay, so show mu f is equal to mu. How do we show this? So recall that mu f is referring to above, that mu f of AB is equal to f of B minus f of A. So let's just write it out. AB is equal to mu, is equal to f of B minus f of A. Let's see. Mm-hmm. So f is equal to mu fb minus fa. This is by definitions, right? And how that relate to mu? Mu. What is mu? Mu is a measurable that is finite and all bounded Boreal sets define this. I think, oh, because we define, recall the definition of f, so we have it here. So, suppose, so let 0 smaller than a, smaller than b. So in this case, where this is equal to mu of 0 b minus mu of 0 a, which is equal to mu of a b. And then we're done, right? Let a smaller than 0 smaller than b. So mu of a b is equal to fb minus fa, which is equal to fb is equal to mu of 0x, sorry, mu of 0 b minus what is fa? Let me see. Fb minus fa, mu of 0 b minus fa. What is fa? Fa is equal to negative mu a 0. Okay, so this is mu of 0 b plus mu of a 0. So we have 0 a b, and this is the interval, and this is the interval. So together they're equal to 0, 0 equal to a b. Okay, and then like 0 a smaller than b smaller than 0. So again we have a b is equal to fb minus fa, which is equal to mu of 0 negative b 0 minus or plus mu of a 0, which is equal to mu of a 0 minus mu of b 0. You draw a line to say this b. You have this minus this, so it's this is equal to ab as desired, and then therefore done.